For big two, what two things? Oh, yeah. You should, you can still, you have to do, you should have to do. For the LEDs. Because we made a comment that's 4 people. For ministry was one of the first. It counts. Like how much.
Okay, so we need to start to get through these slides. So this is going to be more high-level state machines. We're going to go over 2 other high-level state machines. We already went over the soda can dispenser. Here we're going to go over this laser-based distance measure. So the way that the laser-based distance measure is going to work is we're going to click a button, right? It's going to send a laser pulse out. It's going to be reflected off the object that's in front of it and come back and hit the sensor. And the laser moves at light speed, so 3 times 10 to the 8 meters per second. And it travels d times 2, right? Because it goes there and it comes back. So if we calculate we know how long it took and we know how fast the laser is, we can calculate the distance that the distance that it traveled based on the time and the speed, right? And we just have to divide that by 2 because it traveled both there and back, right? So that's how it's going to work. So here are our inputs and outputs for our high-level state machine. We have B, which is a button to begin measurement. We have L, which is the laser output. Is it going to be on or off? We have S, which is our sensor for the laser when it comes back. And then we have D, which is displaying the computed distance. All right. So our high-level state machine, we've declared the inputs, outputs, and now do we need any local storage for keeping track of the time, right? And let's start by just creating the initial state. We'll call it S0. And initial state, we're doing nothing. We're just waiting for the user to input, right? And our local storage to keep track of the time is going to be called dreg. And this is our initial state. Laser is off, distance is reset to 0. Okay. So what should transition us to the next state? Pushing the button. So, well, we just go to the next state no matter what. And then when we're in the other states, we're just waiting for the button to be pushed. Right? So if the button is not pressed, we do nothing. If the button is pressed, then we go to S2. And then in S2, what are the few things that we should do? Yeah, turn the laser. Right? So when we go to S2, we're going to turn the laser on. And we don't need to keep it on, right? It's just going to be a pulse that goes out and then it's going to come back. So then we immediately transition to S3 and turn the laser off. And then while the laser is off, we're going to then wait for the sensor to detect that the laser came back, right? And while we're waiting, this is where we need to keep track of how long it's taking, right? So we're going to use the local storage and we're going to count the number of cycles that it takes for the reflection to come back. So there's our cycle count, and here is our increment for the cycles. All right, once the reflection is detected, then we're going to go to state S4, right? And we're going to stop incrementing the number of cycles. And once we're in state S4, we can also just calculate the distance, right? So if we assume that our clock frequency is 3 times 10 to the 8, which is just the speed of light, then that means that the number of cycles that we were waiting is just the number of meters that the light traveled. So all we have to do to calculate the distance is divide it by 2 because it went to the object and came back. So our output register just becomes our cycle count divided by 2. And once we have that, we can go back to S1 and wait for the button again. So this is our high-level state machine diagram for this. Any questions on it? Okay. So first thing we do is create the data path, right? So what do we need in the data path? What functional units do we need? We need an adder. What else do we need? How do I calculate the distance?
Is that a shifter?
You can make it a shifter. I would shift right by 1, right? Because I just need to divide by 2. You could instantiate a divider, but we only need to divide by 2. So that's why we're going to do a shifter, right? What else do I need? How am I going to keep track of the number of cycles? How am I going to store them? What's it called? Yep, and a register is just multiple flip-flops, right? So I need 2 registers, one for counting and one for what is the calculated output. So here's my 2 registers. They have loads and clears, right? Because I need to be able to clear them. And then I also need to be able to enable them in order to get the new inputs. And over here is when this one is enabled. That's our clears. There's our loads. Here's our adder. And the adder is connected to the counter, right? So we're going to add 1 when it's enabled. And then we need this shifter that shifts right by 1. It just takes the data counter, shifts it right by 1, and that is what gets saved into our output register. So this is my data path. Right? I just need to look at the high-level state machine. What are the different combinational components that I need? And what are the different sequential components that I need? And then all these equations also tell me exactly how they need to be connected, right? data count is data count plus 1. So one of the inputs into the adder is data count, the other is 1. The output is into data count. Dreg is data count divided by 2. So we have that shifter. Question? There's 16 bits. So there's 16 D flip-flops inside them. One for each bit. Right, it's exactly what you did in the counter lab. Okay. Yeah. So the clear just makes it all of the flip-flops or the bits of the register 0. The load just means that I'm going to allow this input to be saved into my flip-flops. If load is 0, then I keep my previous value. Not necessarily. One of them should have precedence though. Right. So like if clear is 1, we don't care what load is, probably. We just make it clear all to zeros. So it's again just like your lab, like you would do based on the if statements. You would have those set. All right. So this is our data path. Next step is comes after the data path.
Table.
How does the data path know when to clear, when to load? When do I want this output from the adder? When do I want the outputs? What is setting these control signals? Indirectly, yes. What is the hardware that is setting these control signals? Huh?
Control panel or the control file?
The control. We need to design the controller. Right? So we have to figure out what is our inputs into the controller, what is our output from the controller. So here's our data path. It requires input of the loads and clears for the registers. It's going to get those from the controller. And then the other thing that goes input into the controller is the button, as well as the sensor. Right? Because those are the things that are defining when we're moving to the next states. And then we have a clock. And we said it's 300 megahertz so that we match the speed of light. So we can just count the number of cycles. All right, so first step to designing our controller is copy and paste the states, right? So we copy and paste all of these states. And then we also need to figure out for each state, what is the required output, right? So we know from the high-level state machine diagram that the laser needs to be 0 on every single state except for S2. Right? And then our transitions are also the same, right? We always transition from S0 to S1. In S1, we wait for the button. Then we transition to S2, transition to S3. In S3, we wait for the sensor. So our states and transitions are all the same. We just need to define what is the outputs for each state. So in S0, we need to clear the output register. And then we have also that everything else doesn't really matter, right? And one other convention is if it's not listed, it's 0. S1, what do we need to do? What does the high level state machine say to do? Well, yeah, we're waiting for, I'm talking about output. What do we need to output?
Same thing as S0.
Not quite. We didn't do something in S0. What does it say to do in S1 here? Remember, dereg and decounter are different.
So it sets the counter to 0.
Yep.
Clears the counter.
We're going to clear the counter. That's it. And then we wait for B. And then when the button is pushed, we output, we turn the laser on, right? Do we need to do anything else? No. Everything else can just stay or stay 0. And the important things are bolded. Everything that's not bold, basically you could just omit it. Because if it's omitted, we assume it's 0, right? So in S3, this is where we're counting, right? We're waiting for the sensor to get the laser come back, right? So because we want to count, that means we need our counter register to be enabled. So load needs to be 1. Because if load is 0, I'm just going to stay 0. But if load is 1, then I get 0 plus 1 is 1. And then next cycle, I get 1 plus 1 is 2. 2 plus 1 is 3. And we keep going until we get the sensor inputs, right? And when we get the sensor inputs, what needs to change?
To be loaded into the package.
So we need to calculate the distance, right? So that means that dereg load is 1, right? And what else do I need to make sure happens?
Turn off the.
Turn off the counter on, right?
Yeah.
So dereg load is 1, decounter load is 0. Right? Because we don't want to increment it anymore. And when dereg load is 1, we take the counter, divide it by 2, and that goes into dereg. Okay. And that's our output. And now once we have there, we go to S1. And it displays the distance in meters, right? So now that we have, this is a finite state machine, right? It has multiple outputs, but it just has 5 states. We could create the K-maps. Well, create the excitation table, then create the K-maps, get the Boolean logic equations, draw the circuit. Okay? Yeah.
Because of the way that this data path is drawn, so every time you count and the Q comes out of the counter, the shifter is already shifting it, right?
Yeah, but we don't care
But it
because
doesn't care
it's
until the load.
because we don't load it. Same thing like with the adder part. It's adding 1 every single time, but we're not always reading it. We're not always saving it into data counter. So like when we're here in S1, we're doing 0 plus 1 every single time, but load is 0. So we keep 0. And then the next cycle it does 0 plus 1. Okay. And same thing, it does 0 divide by 2. But we don't save it. Everybody good with this? All right. So this is just the simplified view, right? We removed all of the things that are not necessary. So we did keep like the laser as 0 here just to indicate that it did turn off. And we also did keep that data counter load does turn to 0 here. Because it's important to know the distinction that it is on here, but when we transition from S3 to S4, once we're in S4, we don't want that load to be on anymore. All right, so this was our design process. We first capture the behavior with the high-level state machine. Then we create the data path. Then we connect the data path to the controller. Then we copy paste the states and the transitions from the high-level state machine, create the finite state machine to get the controller. And then once we have that finite state machine, we can create the circuits, and then we already have them connected from 2B, right?
How come when we get to S4, we don't transition to S0 instead? Because
we want to display the distance until the next measurement. Because if we went from S4 to S0, the D-reg clear is 1. So then the distance would display for 1 cycle. So you wouldn't be able to see it.
follow up. So then would you have to turn the high-level state machine on and off to be able to use it again?
No.
Because won't it remember the distance from?
Because it gets overwritten next time it goes to S4. Right. So you press the button again, it counts again, and then it overwrites the old measurements in S4. And then you go back here. So it gets calculated in S4. It displays in S1. That one is pressed. The counter clears, but the output register, D-reg, doesn't change again until S4. Mm-hmm. Right. So here's our SOTA one again. And the only thing, if we did do all of the K-maps, get our 2-level logic, this is what the finite state machine would look like. This is what the controller would look like. And all we want to mention here is that we can calculate the maximum frequency of these circuits, right? And all we have to do is register to register, evaluate all of them. Which one is the longest path for our minimum clock period or maximum frequency, right? And there are many different paths that exist. Like there's these very short paths, right? From here, from state to state. But there's also these very long paths from state to clear. And then we also have over here from total register through this big adder back into total register. So you have to do all of these different paths, find the maximum, right? And it's not just paths between the controller and the data path. There's paths within the controller. There's paths within the data path. There are paths that can go between them, though. Okay. Right. Here it's just showing some different paths. We already went from state to state, from the state register to the total register, from the total register back to itself. And you use the same sequential logic timing equations, right? Okay, so next example is this video compression example. So the way that this machine wants to work is we want to compare two different frames. And if the difference is very, very small, then we can just send the part that is different, right? So we need a way to calculate how different these two frames are. So the way that we're going to calculate if two frames are different is we're just going to iterate through all of the pixels and subtract them and take the absolute value, right? And get a sum of all the differences. Because if they're the same pixel, the difference would be 0. And then if this sum of the differences is above a threshold, then we'll send a complete second frame. If it's not, we'll send the difference of the frames instead. Is this clear to you guys? Okay. So we're just going to use a small example. So the images are 16 by 16 and they're grayscale. And they're 8 bits each pixel. So we have a 256 byte array, gives me 1 image. So here is my high-level state machine to figure out if we need to send that frame or we can send the differences of the frames. First, we have inputs A and B. They're from memory, right? So A and B are some memory. And then we're having this input go that says that we're going to start. And then we have SAD, which is sum of absolute differences. So this is our output. So in terms of local registers storage, we have the sum, and then we have the registered outputs. And we also have I, and I we're going to use to increment through the different pixels. So first state, our reset state is we go to S0, right? And we're going to wait for the go signal. So if we never get it, we just stay here. But when we see the go signal, we're going to go to S1, reset sum, resets I, and then immediately transition to S2. And then when we're in S2, if I is less than 256, which is the end of the array, then we're going to calculate the difference at that current pixel, right? And we're going to add it to the sum. And then we're going to increment I. Then we go back to S2. And if I is still less than 256, we're not at the end yet. So we need to go to the next pixel. Calculate the difference, add it to the sum. And we go back to S2. And then after 256 iterations, I will be greater than 256 or equal to. So we're going to go to S4. And then our output register just becomes the sum, which is the sum of absolute distances. And then the other controller that is going to determine if we send the full frame or the differences of the frames can now use this sum, compare it with the threshold, and make that decision. But this machine just gets the sum, gets the difference. Okay. Is it clear what each state is doing here? All right. So first step now that we have the high-level state machine is make the data path, right? So this is our data path, right? So we have this comparator is I less than 256. We have 3 registers, our registered outputs, the sum, and our I, which we're using to increment. We need a subtractor to subtract A from B, right? And then we have the absolute value because we care about the absolute difference. And then we have the adder to add the absolute difference to the total sum. Are we good with this data path? You see where every component came from? And we have basically loads and clears, except for our output register. We don't need a clear. We're just going to load. We'll only overwrite it when we have a new frame, right? So next step is control. And again, control is just going to be copy paste the states and transitions. But now we need to convert them to all of these signals in terms of the transitions. And then we also need to set our different outputs. So if we want sum to be 0, really that means some clear signal needs to be 1, right? And if we want I to be 0, that means that I clear needs to be 1, right? And then now rather than having the transition be I is less than 256, we have this input I underscore less LT underscore 256, which is the comparison of I with 256. And then here we wanted to do sum is sum plus the absolute value of A at I minus B at I. In this case, we need to make, in order to save to the sum register, sum load needs to be 1. And then we also need to say that we want to read from the data arrays A and B. So A, B underscore read need to be 1. And then we need to increment I. So I increment needs to be 1. And then in S4, we want our output register to become the sum. So we just need to make sure that the load is 1. Right? And if anything is not shown, it's assumed to be whatever the previous value was or 0, right? So this is our controller. This is our data path. That's how they're connected. We know how to convert this finite state machine into its own data path, right? Yeah.
So it takes from, oh, AV read is the output of the output. Okay, that's when it goes from 2 to 4.
What do you mean 2 to 4?
From state 2 to state 4 is
Oh,
AV read is 1.
no, it's in state S3
Oh, okay.
because A and B are data arrays. So we need to tell it that we want to read from it.
Oh.
So we give it the address, AB address, which is just I, right? And then we say, I want to read. And then we get the data out from those arrays. Mm-hmm.
So the AV adder, so the comparator outputs a 1, like let's say it outputs a 1, does that 1 get inputted into the controller?
Mm-hmm.
Okay.
Because our controller needs to know when I is less than 256. So our data path is going to calculate that for us. So we have I as inputs. And this is a comparator where the second input is always 256. And then if I is less than 256, this would be 1. If I is not less than 256, this would be 0. It would only care if it's in states S2, right? So this again would be your excitation table, right? You have as inputs go and I is less than 256. And then you also have your current state. So you have 5 states, so you need 3 state bits. So then you have 5 input bits. And then in terms of outputs, you have your next state, which is 3 bits. And then you have AB read, I increment, I clear, sum load, sum clear, sad reg load. So you have 9 outputs. So it's a lot of K-maps. I wouldn't ask you to do something like this. Okay. The point is that you know how you would go about it. Right? And you learn from the finite state machine lab that for implementing the control or these finite state machines, I don't need to do these excitation tables, right? I just need to have this. And I can code it in behavioral logic, right?
Because you only care what takes you from state to state.
Yeah.
That one.
Yeah, I only care about what is the behavior. If I'm in this state, this is my input, what is my next state? If I'm in this state, what is my output? Or if I'm a mealy, if I'm in this state and the input is currently this, what is my output? So this is our summary. We have first, from the description of the problem, define the high-level state machine. What's the inputs? What's the outputs? What internal storage do I need? And then I draw the diagram. Then from the diagram, I figure out what is needed in my data path, how my data path is connected. And then again from the diagram, I need to make the finite state machine that creates my controller. I need to connect that controller to the data path. And then the last step is implementing the finite state machine. And once you have the controller, the data path, all of it connected, then you can do this timing analysis. Okay, so that is this lecture. Next lecture, I'm going to go over your lab as well as I'll give you a little bit of a tutorial on the algorithm that you're going to implement for the final project. But we can end here. Your code for today is, what is it? 242. So do just answer the poll before you leave. I can stay here for the 12 minutes for the people that wanted to ask questions.